Imagine a world governed by two sets of rules, each spectacularly successful in its own domain, yet fundamentally incompatible. This isn't the premise of a science fiction novel, but the very real predicament facing modern physics. We have, on one hand, Einstein's general relativity, a theory of gravity that paints the cosmos as a grand, smooth stage, where space and time bend and curve under the influence of mass and energy. It is a triumph of human thought, accurately predicting everything from the bending of starlight around massive objects to the existence of black holes, those cosmic vacuum cleaners from which nothing, not even light, can escape. Then there's quantum mechanics, a theory that governs the bizarre and counterintuitive world of the very small, the realm of atoms and subatomic particles. Here things aren't smooth and continuous, but rather quantized, existing in discrete packets, like grains of sand. Particles can be in multiple places at once, a phenomenon known as superposition, and they can be linked together in a spooky way, even across vast distances, through quantum entanglement. Quantum mechanics has given us lasers, transistors, and nuclear energy, shaping the technology that defines our modern lives. But here's the rub. These two theories, both pillars of modern physics, simply don't play well together. General relativity excels at describing the universe on a grand scale, the dance of galaxies and the evolution of the cosmos. Quantum mechanics, on the other hand, reigns supreme in the microscopic world, explaining the behavior of particles within atoms. When physicists try to combine them to create a single unified theory that describes all of reality, things break down. The mathematics become nonsensical, spitting out infinities and paradoxes. It's like trying to fit a square peg into a round hole, forcing two beautiful and perfectly functional systems to merge, only to create a monstrous dysfunctional hybrid. This cosmic conflict becomes particularly acute in extreme environments, places where both gravity and quantum mechanics are simultaneously important. Think about black holes. General relativity predicts that at the very center of a black hole there exists a singularity, a point of infinite density where the laws of physics as we know them cease to exist. But what happens at the quantum level? Does quantum mechanics offer a way to tame this singularity, to smooth out the infinite sharpness? Or consider the Big Bang, the explosive birth of our universe. At the very first fraction of a second, the universe was incredibly small and incredibly dense, a realm where both gravity and quantum mechanics were in full force. How did the universe transition from this quantum soup to the classical cosmos we observe today? These are questions that our current theories simply cannot answer. The clash between Einstein and the quantum pioneers exposes the limitations of our understanding, revealing that we are missing a crucial piece of the puzzle. Perhaps, as some physicists suspect, space and time themselves are not fundamental, but rather emerge from something deeper, something we have yet to fully grasp. The search for that missing piece has led to some truly radical ideas that challenge our very notions of reality, ideas like string theory. It's a quest to reconcile the infinitely large with the infinitely small, a journey that may ultimately reveal the true nature of the universe. It is a quest that demands we rethink everything we thought we knew. The universe is far stranger, far more mysterious than we ever imagined. So, we're left with a universe that's fundamentally fractured, a jigsaw puzzle with pieces that stubbornly refuse to fit. Einstein's elegant curves clash with the quantum world's jittery uncertainties. It's a crisis, yes, but a crisis that often births revolutionary ideas. And that's precisely where string theory enters the stage, a concept so audacious, so mind-bending, that it could rewrite the very textbooks of physics. What if everything we thought we knew about the fundamental building blocks of reality was, well, just a little bit off? For decades, physicists have operated under the assumption that the universe is built from point particles, infinitesimally small specks of matter with no dimension, existing at a single point in space. Think of electrons, quarks, the fundamental constituents of atoms. They've always been treated as these zero-dimensional objects. But what if, instead of points, the universe was actually composed of something far more vibrant? Imagine replacing those dimensionless points with incredibly tiny, one-dimensional vibrating filaments, loops of energy that resemble miniature, infinitely small strings. This is the central and frankly startling proposal of string theory. It's a shift in perspective so profound that it has captivated physicists for decades, promising a potential resolution to the seemingly intractable conflict between general relativity and quantum mechanics. Now you might be asking, where did this incredibly strange idea come from? It wasn't born out of thin air. It emerged from attempts to understand the strong nuclear force, the force that binds quarks together inside protons and neutrons, the very heart of the atom. In the 1960s, physicists were struggling to explain the behavior of hadrons, particles like protons and neutrons which interact through the strong force. They noticed certain patterns in their interactions that suggested they weren't fundamental particles themselves, but rather were made of something else. One early model, known as the dual resonance model, described these interactions using mathematical equations that oddly resembled the vibrations of a string. It was a promising start, but the model had problems, including the prediction of particles with zero mass, which didn't seem to exist in the real world. The theory was shelved by many, deemed another dead end in the ever-complex world of particle physics. But then, a remarkable thing happened. Physicists realized that those troublesome zero-mass particles could actually be interpreted as gravitons, the hypothetical particles that mediate the force of gravity. Suddenly, this model, originally intended to describe the strong force, had the potential to incorporate gravity, the very force that had eluded unification with quantum mechanics. The seed of string theory was planted, though it would take years of dedicated research to nurture it into the complex and multifaceted framework we know today. These strings, these fundamental building blocks, are not your everyday pieces of twine. They are unimaginably small, far beyond anything we can currently detect, perhaps on the order of the Planck length, which is about 1.6 times 10 to the negative 35 meters. That's a decimal point followed by 34 zeros and then 1/6 meters. To put that in perspective, if an atom were the size of the solar system, a string would be about the size of a tree. They are, in essence, the smallest things imaginable. The revolutionary implication is that what we perceive as different particles, electrons, quarks, photons, are actually just different vibrational modes of the same fundamental string. Change the way a string vibrates, and you change the particle it represents. It's a radical departure from the traditional view of fundamental particles as distinct, point-like entities. It suggests an underlying unity to all the matter and forces of nature. But accepting such a concept requires an extraordinary leap of faith. It requires us to abandon deeply ingrained notions about the nature of reality and embrace the possibility that the universe, at its most fundamental level, is far stranger, far more elegant than we ever dared to imagine. Is this the key we've been searching for? Only time and a lot more research will tell. So, we find ourselves on the precipice of a new understanding. A universe not built of tiny billiard balls, but of something far more melodious. But if these strings are the fundamental building blocks, how do they create the rich tapestry of particles and forces that we observe? Imagine a violin string. Pluck it, and it vibrates at a certain frequency, producing a specific musical note. Change the tension, the length, or how you pluck it, and you get a different note. Now, scale that down to the unimaginably small realm of string theory. Each vibrational mode of a fundamental string corresponds to a different particle. An electron is a string vibrating in one way, a quark in another, a photon in yet another. It's as if the universe is one giant cosmic instrument, with strings vibrating in countless different ways to create all the particles we know and love. Think of it. The electron humming a low note, the top quark screaming high above the staff, even the elusive neutrino perhaps whispering its tune just on the edge of hearing. It's an orchestra of epic proportions, a symphony of existence. But what determines the specific note, the specific particle? It's all in the vibration, of course. The way a string vibrates dictates its properties, its mass, its charge, its spin. Mass, that seemingly inherent property of matter, isn't a fundamental thing in string theory, but rather an emergent property, a consequence of the string's vibrational energy. A string vibrating with more energy will have a higher mass, while a string vibrating with less energy will have a lower mass. Charge, that mysterious property that governs how particles interact electromagnetically, also arises from the string's vibration. The specific pattern of vibration determines whether a string has a positive charge, a negative charge, or no charge at all. It's a breathtakingly elegant picture. Instead of a zoo of fundamental particles, each with its own unique properties, we have a single, unified entity, the string, capable of producing all the particles we observe simply by vibrating in different ways. It's like having a single alphabet that can be used to write countless different stories. The universe, in this view, isn't just a collection of matter and energy, but a vast, intricate, and ever-changing composition. Could the fundamental laws of nature, those seemingly immutable rules that govern the behavior of the universe, be nothing more than the rules of this cosmic music? Are we, in essence, living inside a giant musical instrument where the laws of physics are simply the instructions for how the strings should vibrate? It's a mind-blowing thought, but one that captures the sheer audacity and elegance of string theory. If string theory is correct, it suggests that the universe isn't just playing music, it is music. A symphony of vibrating strings, composing all of reality. Is it any wonder that Albert Einstein, a keen violinist himself, spent his later years searching for a unified theory? Perhaps he instinctively sensed that the universe at its deepest level was governed by principles of harmony and resonance. But maybe it's not harmony that we are hearing. Perhaps it is a beautifully structured, mind-blowing piece of progressive jazz that is so complex we can only perceive the tune through the filter of our 3 dimensions. And with that cosmic symphony resonating in our minds, a crucial question arises. If string theory is indeed the music of the universe, can this elegant framework solve the cacophony of infinities that have plagued physics for decades? Can it truly tame the unruly mathematical beasts that emerge when gravity and quantum mechanics collide? The answer, surprisingly, is yes, and this is where string theory truly began to shine. For years, physicists attempting to merge general relativity with quantum mechanics ran into a brick wall. The calculations, when dealing with point particles, invariably led to infinities, nonsensical results that rendered the theories useless at extremely small scales. Imagine trying to calculate the gravitational force between 2 electrons at a single point in space. The closer they get, the stronger the force becomes, eventually reaching an infinite value, an impossible outcome. It's like trying to divide by 0, a mathematical no-no that signals a fundamental problem with the theory. But string theory offered a way out. By replacing point particles with tiny, extended strings, the interactions between particles are no longer localized at a single point. Instead, they are spread out over a small region of space like a blurry smudge rather than a sharp dot. Think of it like this. Imagine 2 billiard balls colliding. At the moment of impact, they meet at a single point. Now imagine 2 fuzzy clouds colliding. The interaction is no longer instantaneous, but rather a gradual merging and separation of the clouds. This fuzziness of strings, this spreading out of interactions, smooths out the problematic infinities. When 2 strings interact, they join together to form a single string, which then splits apart again. This process is smooth and continuous, without any sharp points or discontinuities. The result is that the calculations, which previously yielded infinite values, now produce finite, sensible answers. It was a monumental breakthrough, a mathematical miracle that suggested string theory was on the right track. This ability to eliminate infinities wasn't just a mathematical trick. It hinted at a deeper, more fundamental understanding of the universe. It suggested that space and time at the very smallest scales might not be as smooth and continuous as we perceive them to be. Instead, they might be fuzzy or grainy, with a minimum size or distance below which the concept of space and time simply ceases to exist. It's a concept that challenges our most basic intuitions about the nature of reality. The mathematical consistency of string theory, its ability to tame these infinities, was one of its first major triumphs, a siren song that drew physicists from around the globe to its banner. It was a sign that this seemingly outlandish idea, this universe built on vibrating strings, might actually be a viable description of the fundamental laws of nature. It offered a glimmer of hope that the long-sought-after unification of gravity and quantum mechanics was finally within reach. This opened doors to solving paradoxes that plagued earlier unification attempts. Picture this. Physicists had been struggling to reconcile the idea of a smooth space-time with the inherent uncertainty of the quantum world. String theory suggested that the uncertainty wasn't just a quirk of measurement, but a fundamental property of space-time itself, smoothed out by the extended nature of strings. A concept previously thought of as contradictory was now potentially resolvable. String theory, in its early days, wasn't just a theory, it was a promise, a beacon of hope in the often murky waters of theoretical physics. Was this finally the path to understanding everything? The journey was just beginning. String theory's mathematical elegance, its ability to banish the infinities that plague other theories, that's a powerful lure. But now, prepare to venture into territory that makes vibrating strings seem almost ordinary. Get ready to confront one of string theory's most audacious and unsettling predictions, the existence of hidden dimensions, extra-spatial dimensions beyond the familiar three we experience every day. Are you comfortable with the idea that everything you've ever known about the shape of reality might be incomplete? For centuries we've been content with length, width, and height. These three dimensions define our world, allowing us to move forward and backward, left and right, up and down. They are the scaffolding upon which our entire understanding of the universe is built. But string theory throws a cosmic wrench into this comfortable picture, suggesting that there may be more to reality than meets the eye. Much more. The mathematics of string theory simply don't work without them. The equations, the very fabric of the theory, demand the existence of extra dimensions, typically 9 or 10 spatial dimensions in total. So, where are they? Have we simply missed them? This initially sparked intense resistance, even ridicule among some physicists. Extra dimensions? It sounded like something straight out of science fiction. After all, we don't see them. We can't travel to them. They seem utterly divorced from our everyday experience. How could a theory so seemingly detached from reality be taken seriously? The question, of course, is not whether we perceive these extra dimensions, but whether the mathematics compels us to accept their existence. Imagine a group of theoretical physicists faced with a mathematical impasse, a problem that simply refuses to yield. Then, a solution emerges, a complex equation that miraculously resolves the conflict. But there's a catch. The equation only works if you add extra variables, variables that represent unseen dimensions. Would you ignore the solution because it challenges your preconceived notions? Or would you embrace the possibility, however strange, that the universe might be more complex, more multifaceted than you ever imagined? The debate continues to this day. Some physicists remain skeptical, arguing that string theory's reliance on extra dimensions is a fundamental flaw, a sign that the theory is detached from reality. Others, however, see it as a necessary consequence of a deeper, more complete understanding of the universe, a glimpse into a reality that transcends our limited human perception. So let's ask the fundamental question, the question that has plagued physicists for decades. If these extra dimensions truly exist, where are they? What are they like? Why can't we see them? The answers, as you might expect, are even stranger than the question itself. So, we're left grappling with this mind-bending concept of extra dimensions. The mathematics scream for them, yet our senses stubbornly insist on only 3. Is the universe playing a cosmic joke on us? Perhaps not a joke, but rather a subtle game of hide-and-seek. String theorists propose a solution, a clever way to reconcile the existence of these hidden realms with our everyday experience. It's called compactification, and it's as ingenious as it is bizarre. Imagine you are walking down a city street. To you, it appears as a one-dimensional line, a path stretching forward. But to an ant crawling along a telephone wire above the street, the world is vastly different. It can move forward and backward just like you, but it can also circle around the wire, exploring a second dimension that is completely invisible to you from your perspective on the street below. Now, imagine that the wire is incredibly thin, so thin that the ant can barely move around it. From a distance, it would appear as if the ant is only moving along a one-dimensional line just like you, but the extra dimension is still there, curled up tightly, hidden from plain sight. This, in essence, is the idea behind compactification. The extra dimensions, according to string theory, are not large and expansive like the 3 we know and love. Instead, they are curled up incredibly tightly, perhaps smaller than an atom, far beyond the reach of our current experimental abilities. They exist all around us, woven into the very fabric of space-time, but they are so small that we simply cannot perceive them. It's like living in a world made of incredibly fine threads, where the extra dimensions are the tiny loops and knots that hold the threads together. We only see the overall fabric, the 3-dimensional surface, but we are blind to the intricate structure that lies beneath. But what shapes do these tiny curled-up dimensions take? This is where things get even more interesting. String theorists believe that these extra dimensions can be shaped into a variety of complex and beautiful geometrical forms known as Calabi-Yau manifolds. These are 6-dimensional shapes, incredibly intricate and complex, that determine the properties of the particles and forces in our universe. It's like the shape of a musical instrument determining the sound it produces. A violin sounds different from a trumpet because of its unique shape. Similarly, the shape of the Calabi-Yau manifold determines the properties of the particles and forces that exist in our universe. These manifolds are not just arbitrary shapes. They must satisfy certain mathematical conditions to ensure that the laws of physics remain consistent. Finding these shapes, mapping them, and understanding their properties is one of the biggest challenges facing string theorists today. Some mathematicians have even devoted their entire careers to studying these exotic geometrical objects, drawn by their beauty and their potential to unlock the secrets of the universe. Let's try another analogy to understand how a large dimension can appear small from a distance. Consider a garden hose. From afar, it looks like a simple, one-dimensional line. But as you get closer, you realize that it has a second dimension, the circumference of the hose. Now, imagine that the hose is incredibly long and thin, stretched out across a vast field. From a great distance, the circumference would be virtually invisible, and the hose would appear as a one-dimensional line, but the extra dimension is still there, curled up tightly, waiting to be discovered. Is it possible that these curled-up dimensions are not just a mathematical curiosity, but a real and fundamental aspect of our universe? If so, it would revolutionize our understanding of everything we thought we knew about reality. It would mean that the universe is far more complex, far more intricate than we ever imagined, a tapestry woven from both the large and the incredibly small, the seen and the unseen. But this opens a Pandora's box. If these extra dimensions can be curled up in different ways, how many different ways are there? And what does that mean for the universe we inhabit? So, These extra dimensions are curled up tighter than the hairs on your head, shaped like geometries that sound more like something out of a science fiction novel than a physics textbook. But if you can curl up these extra dimensions in one way, what's to stop you from curling them up in another? And another? And another? This simple question unlocks a Pandora's box of possibilities, leading us to one of the most perplexing and controversial aspects of string theory, the string landscape. Imagine a vast, undulating terrain, a landscape stretching out to infinity. But instead of mountains and valleys, this landscape is made up of all the possible ways those extra dimensions can be compactified. Each point on this landscape represents a different shape, a different geometry for the hidden dimensions, and each of these shapes corresponds to a different universe with its own unique set of physical laws and constants. It's not just a few possibilities, or even a few million. The estimated number of possible universes in the string landscape is a 1 followed by 500 zeros. That's a number so large, it dwarfs even the estimated number of atoms in the observable universe. This staggering number presents a profound challenge to the very nature of scientific prediction. If string theory predicts almost anything, does it truly predict anything specific about our universe? It's like having a theory that explains every possible outcome, rendering it unable to explain the one outcome we actually observe. If a theory is so flexible that it can accommodate any observation, can it really be considered a scientific theory at all? Think about it. The properties of our universe, the masses of the fundamental particles, the strength of the fundamental forces all seem finely tuned to allow for the existence of life. Change these constants even slightly, and stars might not form, atoms might not hold together, and the universe as we know it would simply cease to exist. For a long time, physicists hoped that a fundamental theory would uniquely predict these constants, explaining why they have the specific values they do. But the string landscape throws a wrench into this dream. If there are countless possible universes, each with its own set of constants, then our universe is just one among an almost infinite number of possibilities, a cosmic accident. This leads to a fundamental question about the uniqueness of our physical laws. Are the laws of physics that govern our universe special, unique, and inevitable consequences of a deeper principle? Or are they simply the result of a random choice, a roll of the dice in the vast casino of the multiverse? It's a question that strikes at the heart of our understanding of the universe and our place within it. The string landscape also lends support, at least in some physicists' minds, to the idea of a multiverse, the idea that our universe is not the only one, but rather just one bubble in a vast foam of countless other universes, each with its own unique properties. Imagine an infinite ocean of universes, each separated from the others, each governed by its own set of laws, each potentially harboring its own forms of life. It's a mind-bending concept, one that challenges our very notion of what it means to be unique and special. Is our universe the only one, a carefully crafted masterpiece governed by unique and inevitable laws? Or is it just one random possibility in a vast and chaotic multiverse, its properties determined by chance rather than necessity? It's a question that continues to fuel debate and drive research in the quest to understand the true nature of reality. The landscape has opened up a new frontier, a realm where the very foundations of physics are being questioned and reevaluated. Is string theory providing a glimpse into the ultimate reality, or has it led us down a garden path of endless possibilities? So we're surrounded by these hidden dimensions, these Calabi-Yau shapes, a universe of possibilities curled up tighter than a tightly wound spring. But what if the story doesn't end there? What if there's another layer of symmetry, a deeper connection between the particles we know and something else? Prepare to enter the world of supersymmetry, or SUSY, a theoretical extension of the Standard Model that proposes a partner particle for every known particle in the universe. Imagine a dance floor. On one side, you have all the familiar particles, the electrons, the quarks, the bosons, each with its own unique spin, its own way of twirling and whirling. Supersymmetry proposes that for every particle on that dance floor, there's a partner, a superpartner, with a spin that differs by 1/2. It's like having a mirror image of the known universe, a shadow world populated by these exotic, yet-to-be-discovered particles. These superpartners are given names that sound like they belong in a science fiction novel. Selectrons, squarks, neutralinos, each a heavier, more exotic version of its ordinary counterpart. But why would nature be so redundant? Why would the universe create a whole new set of particles that we haven't even seen yet? The answer, like many things in theoretical physics, lies in the mathematics. Supersymmetry helps stabilize calculations in string theory, preventing those pesky infinities from reappearing. Remember those infinities we banished by introducing strings? Well, without supersymmetry, they tend to creep back in. Supersymmetry acts as a kind of mathematical bodyguard, ensuring that the equations remain well behaved. Beyond mathematical elegance, supersymmetry offers a tantalizing solution to one of the biggest mysteries in modern physics, the nature of dark matter. You see, we know that the vast majority of matter in the universe is invisible. It doesn't interact with light, and we can only detect it through its gravitational effects. This mysterious substance is called dark matter, and its composition remains one of the biggest unknowns in science. Supersymmetry provides a compelling candidate for dark matter in the form of the lightest supersymmetric particle, often predicted to be a neutralino. These neutralinos, stable and weakly interacting, could have been produced in abundance in the early universe, and would still be floating around today, making up the missing mass. It's as if supersymmetry offers us a chance to solve two major problems in one fell swoop, stabilizing our calculations and solving the mystery of dark matter. So, if supersymmetry is so compelling, if it solves so many problems, why haven't we found these superpartners yet? This is the million-dollar question, or perhaps the multi-billion-dollar question, given the cost of the experiments designed to find them. Physicists have been searching for these elusive particles for decades, using powerful colliders like the Large Hadron Collider, or LHC, at CERN. The LHC smashes protons together at incredibly high energies, recreating the conditions that existed in the early universe. The hope is that these collisions will produce superpartners, allowing us to finally detect them and confirm the existence of supersymmetry. But so far, the LHC has come up empty. No superpartners have been found despite extensive searches. This has led some physicists to question whether supersymmetry is truly a viable theory. Perhaps the superpartners are simply too heavy to be produced by the LHC, requiring even more powerful colliders to be discovered. Or perhaps supersymmetry is realized in a different way than we currently understand, with superpartners that are hiding in plain sight, interacting in ways that we haven't yet anticipated. Regardless of the experimental challenges, supersymmetry remains a crucial ingredient for the mathematical consistency of most realistic string theories. Without it, the theoretical framework begins to crumble. It's as if supersymmetry is the glue that holds the whole thing together. But is that enough? Is mathematical consistency enough to justify believing in a theory that lacks direct experimental evidence? That's a question that has plagued string theory for decades, and it's a question that continues to drive research in the quest to understand the true nature of reality. This is the tightrope walk of modern physics, where experimental facts and theoretical elegance must constantly be reevaluated in the face of new data. The search for these superpartners is not just a hunt for new particles, it's a test of the very foundations of our understanding of the universe. Will the LHC eventually reveal these hidden partners, validating supersymmetry and opening a new chapter in physics? Or will we need to rethink our assumptions and explore alternative theories? And just as the scientific community began to grapple with the mind-bending implications of supersymmetry, a truly bizarre twist emerged. Initial research, rather than converging on a single elegant theory, instead blossomed into not one, not two, but 5 distinct and seemingly consistent superstring theories. It was as if the universe, in its infinite jest, had decided to present physicists with a bewildering array of choices, a veritable string theory zoo. Imagine the scene. Physicists, initially united in their quest for a single, unified theory of everything, suddenly found themselves divided, each championing their own particular version of string theory. There was Type 1, a theory that allowed for both open and closed strings, those tiny vibrating filaments that could either form loops or have ends that dangled freely. Type 2A and Type Y2B, both featuring only closed strings, but differing in the properties of their superpartners, those elusive particles predicted by supersymmetry. And then there were the heterotic theories, SO32 and E8 by E8, exotic hybrids that combined elements of both bosonic string theory, an earlier flawed version of string theory, and superstring theory. It was utter chaos, a proliferation of theories that threatened to undermine the entire enterprise. How could there be 5 different versions of the same theory? Which one, if any, was the correct description of the universe? The confusion was palpable, a sense of disorientation that permeated the physics community. It was as if the map to the unified theory had fractured into 5 separate pieces, each leading in a different direction. The initial excitement that had greeted the discovery of string theory began to wane, replaced by a growing sense of frustration and uncertainty. Some physicists questioned whether string theory was even a viable approach, arguing that the existence of 5 different theories suggested a fundamental flaw in the underlying framework. Others, however, remained optimistic, believing that the 5 theories were merely different facets of a single, deeper underlying theory, like 5 different perspectives on the same object. Each of these theories possessed its own unique features, its own set of particles and forces, its own mathematical quirks. Type 1, with its open strings, allowed for the existence of particles that lived on surfaces, objects known as D-branes, which would later prove to be crucial in understanding the deeper structure of string theory. Type 2A and Type 2B, with their closed strings, differed in the way they treated chirality, the handedness of particles, leading to subtle but important differences in their physical predictions. The heterotic theories, with their unusual blend of bosonic and superstring elements, possessed exceptional mathematical properties, making them particularly attractive to some theorists. The challenge was to understand how these 5 theories were related, to find the underlying principle that connected them all. It was like trying to solve a complex puzzle, with each theory representing a different piece, each with its own unique shape and color. The goal was to fit all the pieces together, to find the unifying picture that lay hidden beneath the surface. Could these 5 theories represent the notes of an even grander symphony, a deeper truth still waiting to be heard? It was a period of intense speculation, a time of bold ideas and daring conjectures. And as physicists wrestled with this perplexing puzzle, they stumbled upon a series of remarkable discoveries that would ultimately revolutionize our understanding of string theory. What were these discoveries, and how did they transform the landscape of theoretical physics? The answers, as always, were far stranger and more profound than anyone could have imagined. The world of theoretical physics, as it turned out, was not converging to a single, beautifully simple solution. Instead, it had fractured into 5 distinct versions of superstring theory, each with its own unique quirks and mathematical landscape. It was a bewildering and frustrating state of affairs, as if the universe was deliberately mocking the efforts of physicists to find a unified theory of everything. But just when it seemed like the entire enterprise was about to unravel, a new hope emerged, a seismic shift in understanding that would forever change the landscape of string theory. This event became known as the Second Superstring Revolution. At the heart of this revolution stood Edward Witten, a brilliant and enigmatic physicist at the Institute for Advanced Study in Princeton. Witten, often described as the smartest physicist alive, possessed an almost supernatural ability to see connections where others saw only confusion. In the mid-1990s, Witten began to explore the relationships between the 5 different string theories, and what he discovered was nothing short of astounding. He realized that these 5 theories, which had previously been viewed as separate and competing, were actually different facets or limits of a single, deeper underlying theory. It was as if 5 different maps, each depicting a slightly different region, were actually showing the same territory from different perspectives. But how could this be? How could 5 distinct theories, each with its own set of rules and mathematical structures, be reconciled into a single unified framework? The answer lay in a concept known as duality. Duality is a mathematical transformation that relates one physical theory to another, often in surprising and unexpected ways. It's like having 2 different languages that describe the same reality. On the surface, the languages may seem completely different, with different words and different grammar, but when you translate them, you realize that they are both telling the same story. In the context of string theory, dualities revealed that the 5 different theories were connected by a web of mathematical relationships. One theory, when taken to its extreme limit, could be transformed into another theory. It was a mind-bending concept suggesting that the seemingly distinct theories were actually different aspects of the same underlying reality. For example, type 1 string theory, with its open and closed strings, was found to be dual to the heterotic SO32 theory. This meant that the physics of type 1 string theory at strong coupling, where the interactions between strings are very strong, was equivalent to the physics of the heterotic SO32 theory at weak coupling, where the interactions are weak. It was a stunning revelation suggesting that the distinction between open and closed strings, which had previously been considered a fundamental difference, was actually just a matter of perspective. These dualities weren't just mathematical curiosities, they had profound implications for our understanding of the universe. They suggested that the properties of space and time, which had previously been considered fixed and absolute, could actually be relative depending on the way we looked at them. They also hinted at the existence of new objects and phenomena that had not been previously considered, such as higher dimensional branes, objects that extended in more than one spatial dimension. Witten's insights, along with the work of other leading string theorists, such as Qumran Vafa and Joseph Polchinski, sparked a revolution in the field. Physicists began to realize that the 5 different string theories were not the end of the story, but rather the beginning. They were just different corners of a vast and unexplored landscape, a landscape that held the key to a deeper understanding of the universe. This unification suggested a more profound structure was yet to be uncovered, a structure that would transcend the limitations of the 5 individual theories and reveal the true nature of reality. But what was this deeper structure? What lay beyond the 5 superstring theories? So, the 5 superstring theories, once thought to be rivals, were revealed to be different perspectives on the same underlying reality. A stunning achievement, but it left physicists with an even bigger question. What is this underlying reality? What is the theory that encompasses all 5 superstring theories as mere approximations? The answer, shrouded in mystery and mathematical complexity, lies in the enigmatic realm of M-theory. M-theory, a name deliberately chosen to be ambiguous, stands as the proposed framework from which the 5 superstring theories emerge. Some speculate the M stands for membrane, others for matrix or even mystery itself, a fitting title for a theory that remains largely uncharted. What we do know is that M-theory aims to be the ultimate theory of everything, the grand unifier of all forces and particles in the universe. But what makes M-theory so revolutionary? The key lies in its embrace of an 11th dimension. That's right, an 11th dimension of space-time. While the 5 superstring theories operate in 10 dimensions, 9 spatial and 1 time, M-theory boldly proposes the existence of an additional spatial dimension, a dimension that had been previously overlooked. Now, imagine trying to visualize an 11th dimension. It's a challenge that strains the limits of human imagination. Our brains, evolved to navigate a three-dimensional world, struggle to grasp the concept of extra dimensions. But mathematics, that powerful language of the universe, allows us to explore realms beyond our direct perception. The introduction of an 11th dimension has profound implications. It suggests that the fundamental building blocks of the universe are not just strings, but also higher dimensional objects called membranes, or brains for short. Think of a brain as a generalization of a string. A zero-dimensional brain is a point particle, a one-dimensional brain is a string, a two-dimensional brain is a membrane, and so on. M-theory proposes that the universe is populated by brains of various dimensions, each interacting with strings and other brains in a complex and dynamic dance. These brains are not just passive objects, they are active participants in the drama of the cosmos. They can vibrate, bend, and even collide, creating ripples and disturbances in the fabric of space-time. What does this mean for our understanding of reality? Well, for starters, it suggests that the universe is far more interconnected than we ever imagined. The 5 superstring theories, once thought to be separate, are now seen as different limits of M-theory, like different projections of the same higher dimensional object. Imagine shining a light on a complex shape from different angles. Each angle reveals a different shadow, a different projection of the original shape. Similarly, the 5 superstring theories are different projections of M-theory, each revealing a different aspect of the underlying reality. The emergence of M-theory has also led to a deeper appreciation of the role of duality in physics. Duality, the concept that two seemingly different theories can actually be equivalent, has become a central theme in string theory. M-theory provides a framework for understanding these dualities, revealing how different theories are related to each other through complex, mathematical transformations. But perhaps the most profound implication of M-theory is its potential to unify gravity with the other fundamental forces of nature. For decades, physicists have struggled to reconcile general relativity, Einstein's theory of gravity, with quantum mechanics, the theory that governs the behavior of particles at the subatomic level. M-theory offers a possible pathway to unification, suggesting that gravity is not a fundamental force, but rather an emergent phenomenon that arises from the interactions of brains in higher dimensions. The 11th dimension, the mysterious brains, the intricate web of dualities, M-theory presents a vision of the universe that is both awe-inspiring and deeply perplexing. It is a theory that challenges our most basic assumptions about the nature of reality, pushing the boundaries of human knowledge. But M-theory remains largely enigmatic. Despite decades of intense research, many of its fundamental properties remain unknown. What are the precise equations that govern M-theory? What are the physical principles that underlie its structure? These are questions that continue to drive research in the quest to understand the ultimate nature of reality. This pursuit may yield insights far beyond our current comprehension. So, the relentless quest to understand the universe at its most fundamental level has led us to strings, vibrating filaments of energy far smaller than an atom. These strings dance in multiple dimensions, hidden from our everyday perception. But what if the universe isn't just a symphony of strings? What if there are other players in this cosmic orchestra, objects far stranger and more exotic than anything we've encountered so far? Prepare to expand your mind, because we're about to venture beyond strings and into the realm of brains. These are not your average, everyday objects. They are higher dimensional entities predicted by the enigmatic M-theory that could hold the key to unlocking the deepest secrets of the cosmos. Think of it this way. If a string is like a one-dimensional line, then a brain is like a membrane, a surface that extends in multiple dimensions. A zero-dimensional brane is simply a point particle, the kind we've been familiar with for decades. A one-dimensional brane is, of course, a string. But then things get interesting. A two-dimensional brane is like a sheet of paper extending in two spatial dimensions. A three-dimensional brane is like a solid object, like you or me, extending in three spatial dimensions. And then the possibilities explode. Branes can exist in even higher dimensions, 4, 5, 6, even 9 dimensions, each with its own unique properties and interactions. These branes, often referred to as membranes, are not just theoretical constructs. They are thought to be fundamental objects in their own right, just as fundamental as strings. But unlike strings, which are confined to vibrating in specific ways, branes are free to move and interact in a much wider range of ways. They can bend, twist, and even collide, creating ripples and disturbances in the fabric of space-time. Perhaps the most mind-blowing aspect of branes is the idea that fundamental strings can actually end on them. Imagine a guitar string that is stretched tight between 2 points. Now, imagine that one of those points is not a fixed object, but rather a brane, a floating, vibrating membrane. The string can end on that brane, its endpoint anchored to the surface. This has profound implications for how we understand the interactions between strings and branes. It suggests that branes are not just passive objects, but rather active participants in the dynamics of the universe, capable of capturing and releasing strings as they move through space-time. But here's where things get truly radical. What if our entire universe, everything we see around us, the stars, the galaxies, the very fabric of space and time, is actually confined to a three-dimensional brane floating within a higher dimensional space? It's a mind-bending idea, one that challenges our most basic assumptions about the nature of reality. Imagine a vast ocean, and on the surface of that ocean, there's a thin layer of oil. That oil represents our three-dimensional brane, our universe. We are confined to the surface of that oil, unable to move up or down, unable to perceive the vastness of the ocean beneath us. All the particles and forces that we know and love, the electrons, the quarks, the photons, are trapped within this brane, unable to escape into the higher dimensional space. This idea, known as brane cosmology, has gained significant traction in recent years, offering a potential solution to some of the biggest mysteries in physics. Why is gravity so much weaker than the other fundamental forces? Why does the universe seem to be expanding at an accelerating rate? These are questions that brane cosmology may be able to answer. The key lies in the fact that while particles like photons and electrons are confined to our brane, gravity may not be. Gravity, according to some theories, is free to propagate into the higher dimensional space, diluting its strength within our brane. It's as if gravity is leaking out of our universe, explaining why it appears so weak compared to the other forces. This also has radical implications. The possibility that particles and forces could be confined to these branes. What if the reason we haven't seen the particles predicted by supersymmetry, those superpartners of the standard model particles, is that they live on a different brane, another universe parallel to our own just out of reach? Are we living in a three-dimensional bubble, oblivious to the vast multi-dimensional reality that surrounds us? Is our universe just one of countless other branes, each with its own unique set of physical laws and constants? And what would happen if two branes were to collide? Could such a collision trigger a new Big Bang, creating a new universe in its wake? These are the questions that keep string theorists up at night, driving them to explore the deepest mysteries of the cosmos. The answers may not be easy to find, but the journey itself is a testament to the boundless curiosity and ingenuity of the human spirit. Are branes the key to a deeper understanding of the universe, or just another piece in the puzzle? And so we find ourselves contemplating universes nestled within universes, dimensions curled up tighter than a spring, all woven together by vibrating strings and enigmatic branes. But what echoes of these cosmic building blocks might resonate from the very beginning, from the cataclysmic event we call the Big Bang? What if string theory, this audacious attempt to rewrite the laws of physics, could shed light on the universe's earliest moments? For decades, the Big Bang has been shrouded in mystery, a singularity where our understanding of space and time breaks down. But could string theory offer a way to peek behind the curtain, to glimpse the universe in its infancy? The conventional Big Bang model, as elegant as it is, encounters a problem at the very start. It posits that the universe began as an infinitely dense, infinitely hot point, a singularity where the laws of physics, as we know them, simply cease to apply. It is a bit like asking what happens if you divide by 0. Our equations break down. String theory offers a tantalizing alternative, a way to resolve this singularity and provide a smoother, more continuous picture of the universe's birth. Instead of a singularity, string theory suggests that the early universe was governed by stringy effects, quantum fluctuations in the fabric of space-time that smoothed out the extreme conditions of the Big Bang. Imagine a raging ocean. From a distance it appears as a smooth surface, but as you get closer, you see the churning waves, the chaotic turbulence that underlies the apparent smoothness. Similarly, string theory suggests that the early universe was not a smooth, featureless point, but rather a seething cauldron of vibrating strings and brains, their quantum fluctuations smoothing out the singularity. One particularly intriguing idea is known as brain cosmology. Remember those brains, those higher dimensional objects that can exist in various dimensions? Well, some physicists speculate that our universe may be just one of many brains floating in a higher dimensional space. And what if, in the early universe, 2 of these brains collided? Such a collision, a cosmic smash-up of unimaginable proportions, could have triggered the Big Bang, igniting the explosive expansion that gave birth to our universe. Imagine 2 soap bubbles gently touching each other. As they merge, the surface area expands rapidly, creating a larger bubble. Similarly, the collision of 2 brains could have released an enormous amount of energy, creating the conditions necessary for the formation of matter, space, and time. But if the Big Bang was triggered by such a collision, what evidence might we find today? Could there be echoes of this primordial event, faint whispers from the dawn of time that could reveal the secrets of brain cosmology? One potential place to look is the cosmic microwave background radiation, or CMB, the afterglow of the Big Bang. This faint radiation, which permeates the entire universe, is like a baby picture of the cosmos, capturing the universe as it was just 380,000 years after the Big Bang. Within the cosmic microwave background radiation, physicists have detected tiny temperature fluctuations, minuscule variations in the heat that provide clues about the universe's early structure. These fluctuations are thought to have been seeded by quantum fluctuations in the very early universe, the seeds from which galaxies and clusters of galaxies eventually grew. Now here's the tantalizing possibility. What if some of these fluctuations were not just random quantum jitters, but rather signatures of stringy effects, echoes of the brain collision that triggered the Big Bang? What if these fluctuations hold the key to unraveling the mysteries of the universe's origin, providing a direct link between string theory and the observable cosmos? Detecting these signatures, however, is an immense challenge. The fluctuations are incredibly faint, buried beneath layers of noise and interference. But scientists are developing ever more sensitive instruments, telescopes designed to peer deeper into the cosmic microwave background radiation, searching for the subtle patterns that could reveal the secrets of the early universe. Imagine a cosmic archaeologist meticulously sifting through the faint whispers of the past, searching for fragments of pottery that could reveal the secrets of a lost civilization. Similarly, physicists are meticulously analyzing the cosmic microwave background radiation, searching for subtle patterns that could reveal the secrets of the Big Bang and the origins of the universe. Are there stringy effects imprinted on the cosmic microwave background radiation? detectable signatures left behind by vibrating strings and colliding brains. Perhaps these subtle variations in temperature and polarization could reveal the universe's deepest secrets. The answers are out there, encoded in the faint whispers of the cosmos, waiting to be deciphered. But could those whispers provide the evidence that could confirm or deny this grand theory? And if string theory does offer a glimpse behind the curtain of creation, what does it say about those cosmic enigmas, those gravitational monsters that lurk in the darkness, black holes? Could string theory provide answers to questions that have baffled physicists for decades? Prepare to delve into the abyss, to confront the ultimate paradox, and to explore how string theory may just offer a lifeline in the face of oblivion. What happens when something falls into a black hole? It seems like a simple enough question, but the answer has profound implications for our understanding of the universe. According to classical physics, anything that crosses the event horizon, the point of no return, is doomed to be crushed into an infinitely small point at the singularity, the black hole's heart. All information about that object, its composition, its structure, its very essence, is lost forever. But here's the rub. Quantum mechanics, the theory that governs the behavior of particles at the subatomic level, tells a different story. One of the fundamental principles of quantum mechanics is the conservation of information. Information in this context is not just data or knowledge, but rather the complete description of a physical system, the arrangement of all its particles and their properties. Quantum mechanics insists that this information cannot be destroyed. It can be scrambled, hidden, or encoded in complex ways, but it must always be preserved. This is the black hole information paradox, a conflict between two of our most successful theories. General relativity predicts that information is destroyed, while quantum mechanics demands that it be preserved. It's like having two laws of nature that directly contradict each other, a cosmic stalemate that has plagued physicists for decades. The paradox was sharpened in the 1970s by Stephen Hawking, the brilliant British physicist who revolutionized our understanding of black holes. Hawking showed that black holes are not completely black, but rather emit a faint radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon, and it causes black holes to slowly evaporate over time. But here's the kicker. Hawking radiation is thermal, meaning it has no information about what fell into the black hole. It's like burning a book and only getting heat and ash, with no way to reconstruct the original text. As the black hole evaporates, all the information about what fell into it seems to disappear completely, violating the fundamental principle of quantum mechanics. This is where string theory enters the picture, offering a potential resolution to the black hole information paradox. One of the key concepts in string theory is the idea of fuzzballs. Instead of a singularity, a point of infinite density, string theory suggests that the interior of a black hole is actually a complex, highly tangled mess of strings and brains, a fuzzy ball of quantum activity. These fuzzballs, as they are known, are not smooth and featureless like the event horizon predicted by general relativity. Instead, they have a complex structure with a surface that is covered in tiny, vibrating strings and brains. The fuzzball proposal suggests that when something falls into a black hole, it doesn't get crushed into a singularity, but rather gets absorbed into the fuzzball, its information encoded in the vibrations of the strings and brains. The Hawking radiation emitted by the black hole is not random and featureless, but rather carries information about the fuzzball's structure, allowing the information to escape over time. It's like burning a book and somehow managing to capture the smoke and ash, analyzing it to reconstruct the original text. A seemingly impossible feat, but one that string theory suggests may be possible, at least in principle. Another key concept is the holographic principle, which suggests that the information content of a volume of space can be encoded on its boundary. Imagine a hologram, a two-dimensional image that contains all the information needed to reconstruct a three-dimensional object. The holographic principle suggests that our entire universe may be like a giant hologram, with all the information about what happens inside encoded on the boundary of the universe. In the context of black holes, the holographic principle suggests that the information about what falls into a black hole is not lost, but rather encoded on the event horizon, the black hole's boundary. The Hawking radiation emitted by the black hole carries this information away, preserving the fundamental principle of quantum mechanics. But perhaps the most compelling evidence that string theory can resolve the black hole information paradox comes from its ability to provide a microscopic description of black hole entropy. Entropy is a measure of disorder or randomness, and black holes, despite their seemingly simple structure, have an enormous amount of entropy. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking showed that the entropy of a black hole is proportional to the area of its event horizon. This was a remarkable result, suggesting a deep connection between gravity, thermodynamics, and quantum mechanics. But what was the microscopic origin of this entropy? What were the fundamental degrees of freedom that gave rise to this enormous amount of disorder? String theory provides an answer. By counting the number of possible configurations of strings and branes within a black hole, string theorists have been able to calculate the black hole's entropy, and their results match perfectly with the Bekenstein-Hawking formula. It was a stunning triumph, a direct confirmation that string theory can provide a microscopic description of black hole thermodynamics. This is like finally understanding the inner workings of an engine, seeing how all the parts fit together to generate power. It provides strong theoretical support for the theory. It gives physicists confidence that string theory is on the right track. But does this mean the paradox is fully resolved? Perhaps more light will be shed on this subject later. But if those fuzzballs somehow manage to encode information and release it back into the universe, what does that say about the very nature of reality itself? What if everything we experience, everything we touch, see, and feel, is not what it seems? What if our three-dimensional world is nothing more than an elaborate illusion, a projection from some distant surface? This is the mind-bending proposition of the holographic principle, an idea born from the depths of black hole physics and nurtured by the fertile imagination of string theory. It suggests that the information content of a volume of space can be entirely encoded on its boundary, like a hologram storing a three-dimensional image on a two-dimensional surface. Think about a standard hologram. You shine a laser on a flat two-dimensional piece of film, and suddenly a three-dimensional image appears to float in mid-air. The holographic principle suggests that our universe may be operating on similar principles, that all the information about our three-dimensional reality is encoded on some distant, two-dimensional surface. But where is this surface? What is it made of? And how does it project our reality into existence? These are questions that have puzzled physicists for decades, leading to some of the most profound and unsettling insights into the nature of the cosmos. One of the most fruitful avenues of exploration has been the anti-de Sitter space, conformal field theory correspondence, more commonly known as ADS/CFT. This is a mathematical framework that connects gravitational theories in higher dimensions with quantum field theories in lower dimensions. Imagine a universe shaped like a saddle, a negatively curved spacetime known as anti-de Sitter space. In this spacetime, gravity behaves in peculiar ways, allowing physicists to explore the connections between gravity and quantum mechanics in a controlled setting. Now imagine that the boundary of this anti-de Sitter space, the edge of the saddle, is a two-dimensional surface. The ADS/CFT correspondence states that the physics happening inside the anti-de Sitter space, including gravity, is entirely equivalent to a quantum field theory living on this two-dimensional boundary. It's like having two completely different descriptions of the same reality, one involving gravity in higher dimensions, the other involving quantum fields in lower dimensions. This correspondence is not just a mathematical trick. It suggests that gravity itself may be an emergent phenomenon, arising from the interactions of quantum fields on the boundary. It's like the experience of watching a film. If we did not know better, we would swear that we see real three-dimensional action unfolding on the screen. But in fact, what is happening is that a two-dimensional film strip is passing by a bright light that projects those images onto a flat surface. Our perception is three-dimensional, but the reality is two-dimensional. But what does this mean for us? Does it mean that our three-dimensional reality is also a projection, a holographic illusion generated from some distant surface? It's a mind-blowing thought, one that challenges our most basic assumptions about the nature of existence. Could it be that what we perceive as reality is merely a shadow, a faint echo of something far more fundamental? Are we, in effect, living inside a giant cosmic hologram where all the information about our lives, our thoughts, our experiences is encoded on some distant surface? If so, what is the nature of this surface? Where is it located? And who or what is projecting our reality into existence? It may sound like a plot from a science fiction film, but the implications of the holographic principle are far-reaching and deeply unsettling. Perhaps there will come a day when we can step through the looking glass and see what's on the other side. But imagine for a moment if our perception is actually being manipulated by some advanced extraterrestrial race. I mean, is that possible? Maybe? Just imagine. But if we live in a holographic universe, then perhaps it's time to ponder an even more perplexing question. If the universe is a symphony of vibrating strings, why is gravity such a faint melody? We see its effects everywhere, holding planets in orbit, shaping the cosmos on a grand scale, yet it's astonishingly weak compared to the other fundamental forces. Think about it. A simple refrigerator magnet can overcome the entire gravitational pull of the Earth to hold a paperclip in place. How can something so pervasive be so incredibly feeble? This is the hierarchy problem, one of the most nagging puzzles in physics. A puzzle that string theory may offer a uniquely elegant solution to. Compared to electromagnetism, the force that governs light and holds atoms together, gravity is weaker by a factor of roughly 1, followed by 39 zeros. That's a truly staggering difference, a disparity that begs for explanation. It's as if the universe is whispering when it comes to gravity, while shouting at the top of its lungs with electromagnetism, the weak and strong nuclear forces. Why this cosmic imbalance? Some string theory models, particularly those that incorporate extra dimensions and brains, propose a radical explanation. Gravity isn't inherently weak. Instead, it only appears weak to us because it's diluted, its strength spread out across dimensions beyond our perception. It's like pouring a glass of water into a vast ocean. The water is still there, but it's so dispersed that it becomes practically undetectable. Imagine our universe as a three-dimensional brain, a membrane floating in a higher dimensional space. The other fundamental forces, electromagnetism, the strong and weak nuclear forces, are confined to this brain, trapped within its boundaries. They can't escape into the extra dimensions. Gravity, on the other hand, is different. Some theories propose that it's free to roam, to propagate through all the dimensions, both those we can see and those that remain hidden. In this scenario, gravity's strength is diluted as it spreads out across the higher dimensional space, making it appear much weaker to us on our three-dimensional brain. It's as if gravity is leaking out of our universe, its power seeping into dimensions beyond our reach. This idea has profound implications. It suggests that the true scale of quantum gravity, the energy at which gravity becomes as strong as the other forces, could be much lower than traditionally thought. For decades, physicists have assumed that quantum gravity would only become relevant at the Planck scale, an energy level so high that it's far beyond the reach of any current or foreseeable experiment. However, if gravity is indeed diluted by extra dimensions, then the true scale of quantum gravity could be much closer, perhaps even within the reach of the Large Hadron Collider or future particle accelerators. This would open up the possibility of directly probing the quantum nature of gravity, of witnessing the interactions of gravitons, the hypothetical particles that mediate the force of gravity. Some models even suggest that the extra dimensions could be relatively large, perhaps even millimeters in size. This might sound astonishing, but remember that these dimensions are curled up, compactified, in such a way that they remain invisible to our everyday senses. But even if they are curled up tightly, the existence of relatively large extra dimensions would have measurable consequences. It could, for example, affect the way gravity behaves at short distances, leading to deviations from Newton's inverse square law, the law that describes how gravity weakens with distance. Scientists are actively searching for these deviations, conducting experiments to measure gravity with unprecedented precision at small scales. What if gravity, that familiar force that keeps our feet on the ground, is just a shadow of something far grander, a whisper across dimensions we can barely comprehend? Could the hierarchy problem be a clue, pointing us towards a deeper, more unified understanding of the universe? Perhaps someday we'll unlock the secrets of these hidden dimensions, revealing the true strength of gravity and the interconnectedness of all the forces of nature. Is it possible that we have been blind all along, unable to see the whole picture because the pieces are so fragmented? So, is gravity just a cosmic stagehand, hidden in the wings while the other forces take center stage? Perhaps. But how do we test these audacious ideas, these mind-bending concepts of extra dimensions and weakened gravity? How do we bring string theory down from the lofty heights of mathematical abstraction and into the realm of experimental verification? The answer, perhaps surprisingly, lies buried deep beneath the Franco-Swiss border in a circular tunnel 17 miles in circumference. Here, at the European Organization for Nuclear Research, or CERN, the Large Hadron Collider, the world's largest and most powerful particle accelerator, is smashing protons together at energies never before achieved. Think of it as a giant cosmic microscope, peering into the smallest scales of reality, probing the fundamental building blocks of matter and the forces that govern their interactions. The Large Hadron Collider is a testament to human ingenuity and collaboration, a project that has brought together scientists from around the globe in a shared quest to understand the universe. It's a technological marvel, a symphony of engineering and scientific precision. But is it sensitive enough to detect the subtle signatures of string theory, to glimpse the hidden dimensions and exotic particles that populate this theoretical landscape? Theorists have identified several potential signals that could indicate the presence of stringy phenomena at the Large Hadron Collider. Perhaps the most eagerly anticipated is the discovery of supersymmetry, those elusive partner particles that are predicted to exist for every known particle in the Standard Model. If supersymmetry is indeed a fundamental symmetry of nature, then these superpartners should be within reach of the Large Hadron Collider's energy range. Their discovery would not only provide strong evidence for supersymmetry, but would also lend credence to string theory, which often incorporates supersymmetry as a key ingredient. But what if supersymmetry remains elusive, stubbornly refusing to reveal itself despite years of intense searching? Does this mean that string theory is wrong? Not necessarily. The absence of supersymmetry at the Large Hadron Collider would certainly be a setback, but it wouldn't be a death knell for string theory. It would simply mean that the energy scale at which supersymmetry becomes manifest is higher than what the Large Hadron Collider can currently probe. Another tantalizing possibility is the creation of microscopic black holes. Now, before you conjure images of miniature cosmic vacuum cleaners devouring the Earth, let me reassure you. These micro-black holes, if they exist, would be incredibly tiny, far smaller than an atom, and they would evaporate almost instantaneously, decaying into a shower of particles that could be detected by the Large Hadron Collider's detectors. The existence of micro-black holes would provide strong evidence for extra dimensions. Remember how gravity might be leaking into extra dimensions, diluting its strength in our three-dimensional universe? If this is true, then the energy required to create a black hole would be lower than traditionally thought, potentially within reach of the Large Hadron Collider. The detection of extra dimensions themselves is another holy grail for physicists working at the Large Hadron Collider. If extra dimensions exist, they could manifest themselves in various ways, such as through the appearance of new particles that propagate in these extra dimensions, or through subtle deviations in the way gravity behaves at short distances. But finding these subtle signals is an immense challenge. The Large Hadron Collider is a noisy environment with billions of particles colliding every second, creating a cacophony of data that must be carefully sifted and analyzed. It's like searching for a single drop of water in the ocean, trying to isolate the faint whispers of string theory from the background roar of particle physics. And what have the results been so far? Well, the Large Hadron Collider has made some groundbreaking discoveries, including the Higgs boson, the particle that gives mass to all other particles. But so far, no definitive evidence for supersymmetry, micro-black holes, or extra dimensions has been found. Does this mean that string theory is on the wrong track? Is it just a beautiful mathematical fantasy with no connection to reality? Perhaps not. The Large Hadron Collider is still in operation, and it's constantly being upgraded to higher energies and luminosities. The search for stringy phenomena continues, driven by the hope that someday, perhaps in the near future, the Large Hadron Collider will finally reveal the secrets of the universe and provide the experimental evidence that string theory so desperately needs. But remember the energy scales that are involved. We are talking about energies that are unfathomable, energies that are reminiscent of the moments just after the Big Bang. The challenge is immense, but the reward for the human race would be even greater. But has string theory been a complete failure so far? Or has it been steering us in the right direction all along? The answers, only time will tell. But has string theory been a complete failure so far? Or has it been steering us in the right direction all along? The answers, only time will tell. But what if the universe itself offered us another way to listen? Not to the echoes of colliding particles, but to the very fabric of space-time itself. Imagine being able to hear the universe not through sound waves traveling through air, but through ripples in the very fabric of space and time, gravitational waves. For decades, these waves were just a theoretical prediction, a ripple in Einstein's theory of general relativity. But now, thanks to incredible advances in technology, we are finally able to listen to the universe in a whole new way. Could these gravitational waves hold the key to unlocking some of string theory's deepest mysteries? Think of gravitational waves as ripples in a pond, but instead of water, they are ripples in space-time, created by accelerating massive objects. When black holes collide, when neutron stars spin rapidly, they create these ripples, these disturbances that propagate through the universe at the speed of light. And these ripples carry information. Information about the objects that created them, about the forces that shaped them, about the very nature of gravity itself. But how can we detect something so subtle, so faint? The answer lies in incredibly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and the future space-based observatory, the Laser Interferometer Space Antenna, or LISA. These detectors use lasers and mirrors to measure the tiniest changes in distance, changes smaller than the width of a proton. Imagine trying to measure the distance between the Earth and the Sun to within the width of a human hair. That's the kind of precision we're talking about. LIGO, with its twin detectors located thousands of miles apart, has already made history, detecting gravitational waves from the mergers of black holes and neutron stars. These detections have not only confirmed Einstein's theory of general relativity, but have also opened up a whole new window on the universe, allowing us to study these cataclysmic events in unprecedented detail. And what about LISA? This future space-based observatory will be even more sensitive than LIGO, able to detect gravitational waves from even more distant and exotic sources, potentially including events that occurred in the very early universe. But could gravitational waves provide clues about string theory? The answer is a resounding yes. String theory predicts that certain cosmic events, particularly those that occurred in the early universe or involve exotic objects like cosmic strings, should produce unique gravitational wave signatures. These signatures could be like fingerprints, telling us about the underlying physics that shaped the universe at its earliest moments. Cosmic strings, for example, are hypothetical one-dimensional objects that are thought to have formed in the early universe during a phase transition similar to the one that created the Higgs boson. These cosmic strings, if they exist, would be incredibly dense, with a mass comparable to that of a galaxy squeezed into a space smaller than an atom. When cosmic strings vibrate or intersect, they should produce bursts of gravitational waves, potentially detectable by LIGO and LISA. Imagine detecting a gravitational wave signal that doesn't match any known astrophysical source, a signal that seems to come from nowhere. Could this be the telltale sign of a cosmic string? A relic from the early universe that could provide direct evidence for string theory? It's a tantalizing possibility, one that keeps physicists searching the skies, listening for the faintest whispers of gravitational waves. String cosmology, the application of string theory to the study of the early universe, also predicts unique gravitational wave signatures. Remember those brain collisions, those cosmic smash-ups that could have triggered the Big Bang? Well, such collisions should have generated a flood of gravitational waves, a primordial background that could still be detectable today. These gravitational waves, if detected, could provide valuable information about the conditions that existed in the early universe, testing our understanding of string theory and brain cosmology. It's like trying to reconstruct a crime scene from the faint traces of evidence left behind, piecing together the events that led to the creation of our universe. The sensitivity required for current and future gravitational wave detectors to test these ideas is astonishing. But the potential rewards are immense. If we can detect these unique gravitational wave signatures, we could finally have experimental evidence that string theory is more than just a beautiful mathematical construct, that it is actually a description of the real world. It would be like finding the Rosetta Stone, unlocking the secrets of the universe and revealing the underlying laws that govern its behavior. Could ripples in space-time carry the secrets of string vibrations? Perhaps these gravitational waves, these faint whispers from the cosmos, are the key to unlocking the universe's deepest secrets, finally allowing us to hear the music of the strings. But could those whispers provide the evidence that could confirm or deny this grand theory? We've journeyed through dimensions unseen, listened for echoes from the universe's dawn, and even peered into the heart of black holes. But a nagging question persists, a challenge that looms large over the entire edifice of string theory. Where's the proof? Where is that smoking gun? That unmistakable experimental confirmation that would elevate string theory from a compelling theoretical framework to an established cornerstone of physics. This is, without a doubt, the most significant hurdle facing string theory today: the conspicuous absence of direct, unambiguous experimental evidence. For a theory that purports to describe the fundamental nature of reality, that claims to be the theory of everything, the lack of observational support is a glaring omission. The energy scale at which strings are believed to vibrate, their characteristic frequency, is likely far beyond anything we can currently achieve with our most powerful particle accelerators. Remember, those strings we are talking about are unimaginably small. To directly observe a string, to witness its vibrations, we would need to probe distances on the order of the Planck length, that incredibly tiny scale that is a mere 1.6 times 10 to the negative 35 meters. This would require energies trillions of times greater than what the Large Hadron Collider can muster. It's like trying to see an atom with the naked eye. The scale is simply too small, the energy requirements too immense. This has led to a persistent criticism of string theory, that in its current state, it makes few concrete, testable predictions about phenomena that we can actually observe. A scientific theory, according to the traditional view, should be able to make specific predictions about the outcome of experiments. These predictions can then be tested, and if they are confirmed, the theory gains support. If they are disproven, the theory must be modified or abandoned. But string theory, in its present form, struggles to make such predictions. The sheer complexity of the theory, the vastness of the string landscape with its almost infinite number of possible universes, makes it difficult to isolate specific, testable consequences. It's like trying to predict the weather a year in advance. The number of variables is simply too great, the system too complex. This has led to a vigorous, ongoing debate within the scientific community about whether string theory is truly scientific. Some argue that it is a legitimate branch of theoretical physics, a valuable tool for exploring the fundamental laws of nature, even in the absence of direct experimental evidence. They point to the theory's mathematical elegance, its ability to unify gravity with quantum mechanics, and its potential to solve some of the deepest mysteries of the universe. Others, however, are more skeptical. They argue that a theory that cannot be tested, that cannot be falsified, is not truly scientific. They worry that string theory has become too detached from reality, too focused on mathematical abstractions, and that it may be leading physicists down a blind alley. What, they ask, is the difference between string theory and philosophy, if neither one can be proven wrong? This challenge is best described by physicist Wolfgang Pauli's famous quote when he deemed a colleague's theory as not even wrong. The debate rages on, and it brings us to the topic of testability and its core importance to any scientific theory. It all comes down to being able to prove a hypothesis is wrong. Some suggest it is more important to be able to prove a theory is wrong than prove it to be right. The debate is a delicate balancing act between theoretical innovation and empirical validation, a tension that has always been at the heart of scientific progress. So, how do we move forward? How do we bridge the gap between theory and experiment, between the mathematical elegance of string theory and the tangible reality of the observable universe? So, we're left grappling with a theory that promises to unlock the universe's deepest secrets, yet struggles to produce tangible evidence. But what is it about string theory that continues to captivate some of the brightest minds in physics, despite this experimental void? The answer, in large part, lies in its sheer breathtaking mathematical elegance. Imagine a symphony of equations, each perfectly in tune, harmonizing to create a structure of unparalleled beauty and consistency. This is the allure of string theory, a framework where the laws of physics emerge not from arbitrary rules, but from the intrinsic logic of mathematics. It's a siren song, a call to the aesthetic senses that resonates deeply with those who seek to understand the universe at its most fundamental level. It's a structure that is not only mathematically elegant, but potentially capable of unifying physics itself. But can mathematical beauty alone be a guide to physical reality? Should we place our faith in a theory simply because it's pleasing to the eye or to the mind? This is a question that has vexed scientists and philosophers for centuries, a tension between the abstract realm of mathematics and the concrete world of empirical observation. Therein lies a philosophical debate that has raged in the halls of academia. Consider the words of Hermann Weyl, a towering figure in 20th century mathematics and physics. My work always tried to unite the truth with the beautiful, but when I had to choose one or the other, I usually chose the beautiful. It's a sentiment that captures the essence of this debate, the belief that the universe, at its heart, is governed by principles of beauty and harmony. But history is littered with examples of beautiful theories that turned out to be wrong. The ancient Greeks, for instance, believed that the planets moved in perfect circles, a geometrically pleasing idea that ultimately proved to be inconsistent with observation. For centuries, scientists believed in the luminiferous ether, a medium for the propagation of light. It was mathematically convenient, but ultimately non-existent. And yet, there are also instances where mathematical elegance has served as a compass, guiding physicists toward profound discoveries. In the 1920s, Paul Dirac, a British physicist, formulated an equation that elegantly combined quantum mechanics with special relativity. The equation predicted the existence of antimatter, particles with the same mass but opposite charge as ordinary matter. At the time, antimatter was purely theoretical, a mathematical curiosity. But a few years later it was discovered experimentally, confirming Dirac's prediction and solidifying his place in the annals of physics. Similarly, Einstein's theory of general relativity, with its curved space-time and its mind-bending predictions about the bending of light and the existence of black holes, was initially met with skepticism. But its mathematical elegance and its ability to explain certain anomalies in the orbit of Mercury ultimately convinced the scientific community of its validity. One could say that Albert Einstein composed a beautiful melody, and nature seemed to dance along to it. So, should mathematical consistency alone guide our belief in a physical theory? Is it enough for a theory to be beautiful, even if it lacks direct experimental support? Perhaps the answer lies in a delicate balance, a recognition that both mathematical elegance and experimental verification are essential ingredients for scientific progress. Mathematical beauty can be a powerful guide, pointing us towards promising avenues of exploration, but it must always be tempered by the rigor of experimental testing. Perhaps string theory is simply ahead of its time, a glimpse into a future where our experimental capabilities have caught up with our theoretical ambitions. Or perhaps it is a dead end, a beautiful but ultimately misguided attempt to understand the universe. The jury is still out, and the debate continues to rage. But what cannot be denied is the power of mathematical elegance to inspire, to motivate, and to guide the quest for knowledge, a quest that has driven humanity for centuries and will continue to do so for generations to come. So, we're left grappling with a theory that promises to unlock the universe's deepest secrets, yet struggles to produce tangible evidence. But what is it about string theory that continues to captivate some of the brightest minds in physics, despite this experimental void? The answer in large part lies in its sheer, breathtaking mathematical elegance. But is beauty enough? It's a question that's echoed down the ages, from the ancient Greeks seeking perfection in geometry to modern physicists pursuing a theory of everything. Perhaps, though, the pursuit of a single unified theory is itself a fool's errand. Is string theory truly the only game in town? The truth is, the quest to reconcile gravity with quantum mechanics is a vibrant and competitive field, with a host of alternative approaches vying for attention. String theory might be the loudest voice, but it's certainly not the only one singing in the choir. Let's not forget the significant criticisms leveled against string theory, whispers that sometimes become shouts in the halls of academia. The landscape problem, the sheer number of possible universes predicted by the theory, raises concerns about its predictive power. If string theory can predict almost anything, does it really predict anything at all? The lack of testability, the difficulty of designing experiments to directly verify its predictions, continues to be a major stumbling block, and the complexity of its mathematics, the labyrinthine equations that only a handful of experts can truly understand, can be intimidating and isolating. But these criticisms, while valid, don't invalidate the entire enterprise. They simply highlight the challenges and complexities of modern physics. Perhaps a fresh perspective is needed, a radical new approach that challenges the very foundations of our understanding. One such alternative, and perhaps the most prominent, is loop quantum gravity. Imagine space-time itself not as a smooth, continuous fabric as Einstein envisioned, but as a discrete quantized structure made up of tiny, indivisible units like atoms of space. This is the central idea behind loop quantum gravity, or LQG. In LQG, space-time is woven from a network of interconnected loops, forming a kind of quantum foam. These loops are incredibly small, on the order of the Planck length, that same minuscule scale that haunts string theory. Unlike string theory, which postulates extra dimensions, loop quantum gravity sticks to the 4 dimensions we know and love, 3 spatial and 1 time. It doesn't require supersymmetry or exotic particles. Instead, it focuses on quantizing gravity directly, applying the principles of quantum mechanics to the fabric of space-time itself. This offers a tantalizing prospect of explaining the nature of the universe without adding ingredients that still cannot be verified. One of the key goals of loop quantum gravity is to resolve the singularities that plague general relativity, those points of infinite density that exist at the center of black holes and at the beginning of the universe. By quantizing spacetime, LQG attempts to smooth out these singularities, replacing them with a more gentle, continuous picture. Think of it as replacing a sharp, jagged peak with a rounded, rolling hill. Loop quantum gravity also offers a unique perspective on the Big Bang. Instead of a singularity, a point of infinite density, LQG suggests that the universe may have emerged from a quantum bounce, a transition from a previous contracting phase to the current expanding phase. Imagine a balloon being squeezed smaller and smaller until it reaches a minimum size and then suddenly bouncing back, expanding rapidly outwards. But loop quantum gravity is not without its challenges. It's a complex and mathematically demanding theory, and it has yet to make any concrete, testable predictions that can be verified experimentally. And that's what it boils down to, doesn't it? Is beauty enough to suffice, or is confirmation what's truly required? The truth is that the quest for a unified theory of everything is an ongoing journey, a marathon rather than a sprint. String theory and loop quantum gravity represent just two of the many approaches being explored, each with its own strengths and weaknesses, its own passionate advocates and vocal critics. The fundamental assumptions and goals of these different approaches often differ significantly. String theory, with its emphasis on extra dimensions and supersymmetry, seeks to unify all the forces and particles of nature within a single, elegant framework. Loop quantum gravity, with its focus on quantizing space-time directly, aims to resolve the singularities of general relativity and provide a consistent picture of the early universe. Perhaps ultimately, the answer lies not in choosing one theory over another, but in finding a way to combine their insights, to synthesize their strengths into a more complete and comprehensive picture of reality. Perhaps the ultimate theory will incorporate elements of both string theory and loop quantum gravity, along with ideas from other approaches, creating a synthesis that transcends our current understanding. Is it possible to reconcile the seemingly irreconcilable, to bridge the gap between string theory's elegant mathematics and loop quantum gravity's focus on quantizing space-time? Only time and further research will tell. But one thing is certain: the quest for a unified theory is far from over. Is there room for both to live harmoniously, or will one eventually win out in the scientific arena? So, the scientific arena is filled with the clash of titans, each vying for dominance in the quest to unveil the ultimate truth. Now, stepping away from the collider experiments and quantum bounces, could there be another, perhaps unexpected, arena where string theory is making its mark? What if the ripples of this theory, born from physics's deepest conundrums, are creating waves far beyond the boundaries of the physical world, specifically within the realm of pure mathematics? It might seem counterintuitive at first. String theory, after all, is an attempt to describe the physical universe. Mathematics, on the other hand, often exists in its own abstract plane, independent of the physical world. However, the relationship between physics and mathematics has always been a complex, symbiotic one. Physics provides the questions, the challenges that push mathematics to new heights. Mathematics, in turn, provides the tools, the language that allows physicists to express their ideas and make predictions. String theory is a prime example of this fruitful interplay. The theory's intricate mathematical structure has led to profound insights into pure mathematics, solving long-standing problems and opening up entirely new avenues of research. It's as if the universe, in its infinite wisdom, has whispered secrets to physicists, secrets that mathematicians are only now beginning to decipher. One of the most striking examples of string theory's impact on mathematics is the concept of mirror symmetry. Imagine a pair of geometrical shapes, each incredibly complex, each existing in 6 dimensions, those hidden dimensions that string theory so often invokes. These shapes, known as Calabi-Yau manifolds, are mirror images of each other, like reflections in a cosmic mirror. But here's the twist. While the two shapes look different, their underlying mathematical properties are identical. They are topologically distinct, meaning they cannot be smoothly deformed into one another, yet they share the same essential characteristics. This seemingly bizarre phenomenon, predicted by string theory in the late 1980s, came as a complete surprise to mathematicians. They had no prior reason to suspect that such a symmetry existed. But string theory, with its unique perspective on geometry and topology, predicted that these mirror manifolds should exist, and that they should be related in a profound way. This prediction sent shockwaves through the mathematical community, sparking a flurry of research aimed at understanding the origins and implications of mirror symmetry. Mathematicians soon discovered that mirror symmetry had far-reaching consequences, providing a powerful tool for solving problems in enumerative geometry, a branch of mathematics that deals with counting geometrical objects. For example, enumerative geometry seeks to answer questions like, how many rational curves of a given degree lie on a given Calabi-Yau manifold? These are notoriously difficult problems, often requiring years of painstaking calculation. However, mirror symmetry provided a shortcut, allowing mathematicians to translate these problems into equivalent problems on the mirror manifold, which were often much easier to solve. It's like having two different languages for describing the same reality. One language may be cumbersome and difficult to use, while the other is elegant and efficient. Mirror symmetry allows mathematicians to translate problems from the difficult language to the easy language, making them much more tractable. This has led to a flurry of breakthroughs in enumerative geometry, solving problems that had been open for decades and opening up entirely new areas of research. But the impact of string theory on mathematics goes far beyond mirror symmetry. The theory has also led to new insights into topology, the study of shapes and their properties, and representation theory, the study of symmetries and their mathematical representations. It's as if string theory has provided mathematicians with a new lens through which to view the mathematical world, revealing connections and relationships that were previously hidden. This fruitful interplay between theoretical physics and mathematics is a testament to the power of interdisciplinary collaboration. It shows how the quest to understand the universe can spur innovation in abstract thought, leading to breakthroughs that benefit both physics and mathematics. Think about it. The abstract world of mathematics, seemingly divorced from the everyday experiences of the physical world, has been profoundly shaped by a theory attempting to explain the very fabric of reality. Is it not a testament to the interconnectedness of knowledge, a reminder that the pursuit of understanding often transcends the boundaries of individual disciplines? What other seemingly disparate fields of knowledge might hold the key to unlocking further secrets of the universe? But what other seemingly disparate fields of knowledge might hold the key to unlocking further secrets of the universe? Now consider this. Are the laws of physics simply a cosmic accident? A fortunate roll of the dice that allowed us to exist? Or is there something more profound at play? Some underlying principle that dictates the specific values of the fundamental constants that govern our universe? This brings us to one of the most controversial and philosophically charged ideas in modern physics, the anthropic principle. Imagine for a moment that you are standing before an enormous lottery machine filled with universes, each with its own unique set of physical laws. Some universes are hot and empty, devoid of stars and galaxies. Others are cold and chaotic, with particles flying apart before they can even form atoms. And then there's our universe, a seemingly improbable oasis of stability and complexity perfectly suited for the emergence of life. But why? Why are the constants of nature so finely tuned to allow for our existence? The anthropic principle at its core suggests that we observe our specific universe because its properties are necessary for life to emerge and, crucially, to observe it. In other words, if the constants of nature were even slightly different, we wouldn't be here to ask the question. It's a deceptively simple idea, but one that has sparked intense debate among physicists and philosophers alike. Think about the strength of gravity. If it were even slightly stronger, stars would burn too quickly, exhausting their fuel before life could evolve. If it were even slightly weaker, stars wouldn't form at all, leaving the universe dark and lifeless. Or consider the mass of the neutron. A slight increase in its mass would render all atoms unstable. A slight decrease and there would be no neutrons in the universe at all. The universe really does seem to be balanced on a knife edge. It is almost as if some cosmic chef has fine-tuned all the ingredients, and if he added just a tiny amount more salt, the whole dish would be ruined. But here's where the string landscape comes back into play. Remember that vast, undulating terrain of possible universes, each with its own unique set of physical laws? The string landscape provides a context for the anthropic principle, suggesting that our universe is just one among an almost infinite number of possibilities, a cosmic accident that happened to get the constants of nature just right. Does the landscape, with its staggering number of possibilities, make anthropic arguments almost inevitable? If there are countless universes, each with its own set of constants, then it becomes almost certain that at least one of those universes will have the right conditions for life to emerge. And that, of course, is the universe we find ourselves in. It's a bit like winning the lottery. The odds of winning are incredibly small, but if enough people buy tickets, someone is bound to win eventually. But this raises a troubling question. If the constants of nature are simply a matter of chance, does it undermine the predictive power of physics? For centuries, physicists have strived to find a theory that uniquely predicts the values of these constants, explaining why they have the specific values they do. But if the anthropic principle is correct, then this dream may be unattainable. Perhaps there is no fundamental reason why the constants of nature have the values they do. Perhaps they are simply the result of a random choice, a roll of the dice in the vast casino of the multiverse. Some physicists find this idea deeply unsatisfying. They yearn for a deeper explanation, a more fundamental principle that would explain the origin of the constants of nature. As Einstein himself famously asked, did God have any choice when he created the universe? The anthropic principle suggests that perhaps God had many choices, and we just happen to find ourselves in the one that allows us to exist. The anthropic principle has faced a deluge of scientific and philosophical criticisms. It has been accused of being unscientific, of abandoning the quest for explanation, and of resorting to a kind of cosmic shrug. Critics argue that it is simply a way of avoiding the hard questions, of giving up on the search for a more fundamental theory. Ah, well, it is what it is, they seem to say. They worry that it could also stifle scientific creativity, discouraging physicists from seeking deeper explanations for the origin of the constants of nature. Perhaps it is a case of accepting our limitations. Perhaps we are simply not equipped to comprehend the true nature of the universe, to understand the reasons behind its seemingly improbable existence. In the end, the anthropic principle serves as a powerful reminder of our place in the cosmos, a reminder that we are both observers and participants in the unfolding drama of the universe. It also reminds us that we are made of star stuff, and in some way the universe has conspired to bring us to this point. But does it ultimately leave us with more questions than answers? It is almost as if every answer only opens up another can of worms, each more complex than the last. So we stand at a crossroads, gazing out at a universe of vibrating strings, hidden dimensions, and the faint whispers of gravitational waves. Is this the ultimate destination? Have we finally stumbled upon the long-sought-after theory of everything, the key that unlocks all the secrets of the cosmos? Or is the pursuit of such a theory a fool's errand, a mirage that will forever elude our grasp? For centuries, physicists have dreamed of a single, elegant equation that could describe all the fundamental forces and particles in the universe, a theory that would unify gravity with quantum mechanics, a theory that would explain everything from the smallest subatomic particle to the largest supercluster of galaxies. It is a seductive vision, a testament to the human desire for order and understanding. But is it ultimately achievable? String theory, with its ambitious scope and its intricate mathematical structure, represents the latest and perhaps the most audacious attempt to realize this dream. But after decades of intense research, after countless hours of calculation and speculation, the question remains: how close are we to actually achieving a theory of everything? The progress has been undeniable. String theory has provided profound insights into the nature of gravity, quantum mechanics, and the relationship between them. It has led to new discoveries in pure mathematics, and it has sparked countless new avenues of research. But the hurdles that remain are immense. The lack of direct experimental evidence continues to be a major stumbling block. The string landscape, with its vast number of possible universes, raises concerns about the theory's predictive power. And the complexity of its mathematics makes it difficult for all but a handful of experts to fully understand. So, is it even possible to achieve a theory of everything? Is there a limit to human knowledge, a point beyond which we cannot penetrate? Will science always uncover deeper layers of reality, revealing new mysteries that defy our current understanding? Perhaps the universe is simply too complex, too chaotic, too unpredictable to be captured in a single, elegant equation. Perhaps the laws of physics are not fixed and immutable, but rather evolve over time, changing with the expansion of the universe. Or perhaps there are fundamental limitations to our ability to observe and measure the universe, limits that prevent us from ever gaining a complete understanding of its workings. Consider the words of Kurt Gödel, a towering figure in 20th century mathematics who proved that within any sufficiently complex formal system there will always be statements that are true but cannot be proven. Gödel's incompleteness theorems, as they are known, have profound implications for our understanding of knowledge and its limits. Could it be that the universe, with its infinite complexity, is simply too vast, too intricate for our finite minds to fully comprehend? Are we like ants trying to understand the workings of a skyscraper, able to grasp only a tiny fraction of the overall structure? Or is it more like an Escher painting where, as soon as you think you know how it works, your perception is challenged with new angles and impossible forms? But even if achieving a theory of everything is ultimately impossible, the quest itself is not without value. The search for a unified understanding of the cosmos has driven some of the greatest scientific advances in history. It has led to new technologies, new medicines, and new ways of thinking about the world. And perhaps the most important thing is the human drive to find a final, unified understanding of the cosmos. This relentless pursuit of knowledge is what sets us apart, what makes us human. It is what drives us to explore the unknown, to push the boundaries of our understanding, and to never give up on the quest to unravel the mysteries of the universe. After all, the most astonishing human breakthroughs have arrived by relentlessly questioning the status quo and reaching for an understanding that had long been considered an impossible goal. Even if we never achieve a theory of everything, the journey will have been worth it. The knowledge we gain along the way, the discoveries we make, and the insights we uncover will enrich our lives and expand our understanding of the universe and our place within it. Imagine, if you will, that the very pursuit of this elusive understanding is itself the destination, and it is the journey that gives the ultimate meaning to our quest. So, we find ourselves poised on the edge of scientific discovery, or perhaps just adrift in a sea of theoretical possibilities. But if string theory and its associated concepts remain frustratingly out of reach for direct experimental confirmation, there's another realm where these ideas have taken root and flourished, the vibrant landscape of popular culture. But how do ideas so complex find their way into the collective consciousness? From science fiction literature to blockbuster films, the mind-bending concepts of string theory, extra dimensions, and multiverses have captured the public imagination in ways that few scientific theories ever have. It's a testament to the power of these ideas, their ability to ignite our curiosity and challenge our perceptions of reality. But what happens when these complex scientific concepts are filtered through the lens of popular media? Are they accurately portrayed? or are they simplified and dramatized to the point of distortion? Consider the 1994 episode of Star Trek The Next Generation titled Parallels. In this episode, Lieutenant Worf begins shifting between countless parallel realities, each slightly different from the last. One minute he is celebrating his anniversary with Deanna Troi. The next he is married to Beverly Crusher. The Enterprise is alternately at peace with and at war with the Romulan Empire. The episode serves as a rather accessible and easily grasped, if simplified, analogy to the multiverse concept often discussed within string theory. It is a concept so powerful that it can alter the entire reality of someone as intimately involved in the fabric of space-time as Worf. Then we have films like Interstellar, where the protagonists navigate through a wormhole, a shortcut through space-time that bends the rules of physics, traveling to other galaxies and even falling into a black hole, which presents itself as a tesseract, allowing a character to travel through time and space. These themes are, of course, central to string theory and the search to prove its legitimacy. Interstellar even sought the advice of theoretical physicist Kip Thorne, a Nobel laureate, to ensure the scientific accuracy of its mind-bending visuals, bringing an unprecedented level of scientific rigor to the realm of science fiction. However, the influence of string theory extends far beyond the realms of science fiction. The concept of extra dimensions, for example, has permeated popular culture in a variety of ways, from fantasy novels where characters travel to alternate realms, to video games where players explore hidden levels and secret worlds. Even music has been touched by string theory. The concept of vibrating strings as the fundamental building blocks of the universe has inspired musicians to create compositions that explore the themes of harmony, resonance, and the interconnectedness of all things. How many of these artists realize that their inspirations come from the complex and often inaccessible realm of physics? But the popularization of scientific concepts is not without its challenges. When complex ideas are simplified and dramatized for a mass audience, there is always the risk of misrepresentation and misunderstanding. The nuances of string theory, the mathematical complexities, the experimental challenges are often lost in translation, replaced by sensationalized depictions of alternate universes and time travel. What do people really think of string theory after watching such shows? The average viewer is unlikely to understand the intricacies of the equations, yet they are being presented with information that claims, at least in principle, to represent reality as it is understood by some of the world's most prominent physicists. What is the effect of this? Take the idea of multiple universes, for example. In science fiction, the multiverse is often portrayed as a playground, a place where anything is possible, where there are no consequences for our actions. But in string theory, the multiverse is a much more complex and subtle concept, a vast landscape of possibilities governed by mathematical laws and physical constraints. This distinction is often lost on the casual viewer, leading to a distorted understanding of the scientific concept. There's also the danger of oversimplification. String theory is a highly technical and complex subject, requiring years of dedicated study to fully grasp. But popular media often presents it in a way that is accessible to a general audience, often at the expense of accuracy and detail. This can lead to a superficial understanding of the theory, a sense of knowing without truly knowing. But despite these challenges, the popularization of string theory and related concepts can also have a positive impact. It can spark curiosity about science, inspiring young people to pursue careers in physics and mathematics. It can also broaden our understanding of the universe, challenging our assumptions about reality and opening our minds to new possibilities. Perhaps the greatest challenge lies in accurately communicating these abstract concepts to a wider audience, in finding ways to bridge the gap between the technical jargon of physics and the everyday language of popular culture. Carl Sagan, with his eloquent prose and his infectious enthusiasm for science, showed that it is possible to communicate complex ideas in a way that is both accessible and engaging. Neil deGrasse Tyson carries that mantle forward today, but can their success be replicated? What is the net effect of string theory as presented in popular culture? Do the dramatized and often inaccurate portrayals help or hinder the acceptance of the theory as a potential description of reality? The answer lies in the role of popularization in shaping public perception of cutting-edge physics, a phenomenon that is both fascinating and complex. But perhaps the most important question is this: can these simplified depictions inspire future scientists, igniting a spark of curiosity that leads them to pursue a deeper understanding of the universe? So, as we digest the possibility that our perceived reality is nothing more than a holographic projection, a question begs to be asked. What happens now? Where does the quest to unravel the universe's deepest secrets take us from here? After all, even with its challenges, string theory has provided a framework that allows physicists from all over the globe to tackle what were once considered to be unachievable mathematical impossibilities. It has pushed the boundaries both in math and in theoretical physics. The truth is, the search for a unified theory is far from over. We stand on the shoulders of giants like Einstein and Hawking, but there's still a long road ahead. Ongoing research in string theory and related fields is tackling some of the most fundamental theoretical challenges imaginable. Can we tame the string landscape, finding a way to make concrete predictions about our universe? Can we find a more elegant formulation of M theory, unlocking its deepest secrets? And can we finally reconcile string theory with loop quantum gravity, merging the best aspects of both approaches? But perhaps the most exciting prospect lies in the potential for future experiments to provide new clues. Next-generation colliders, even more powerful than the Large Hadron Collider, could potentially reach energy scales high enough to directly produce superpartners, micro-black holes, or even evidence of extra dimensions. Imagine recreating the conditions just moments after the Big Bang within the confines of a 17-mile tunnel beneath the Franco-Swiss border. And it's not just particle physics that holds promise. Cosmological observations peering deeper into the cosmic microwave background radiation or searching for unique gravitational wave signatures could reveal echoes of the early universe, providing valuable information about the conditions that existed in the moments after creation. After all, if we are to truly understand the universe, perhaps it's best to look to the early stages of development, when the rules of the universe were still forming, where the cosmic clay was at its most malleable. But the world of theoretical physics is not static. New ideas are constantly emerging, challenging our assumptions and pushing the boundaries of our understanding. Perhaps there will be unexpected breakthroughs, radical shifts in perspective that will completely transform the landscape of quantum gravity research. Perhaps we will discover new mathematical tools, new experimental techniques that will allow us to probe the universe in ways we never thought possible. Maybe one day we will create a microscope so powerful that we could not only see an atom, but delve into the secrets that make up that atom. The pursuit of knowledge is a journey, not a destination. It's a winding road filled with twists and turns, with moments of triumph and moments of frustration. But the search for a deeper understanding of reality continues unabated, driven by the insatiable curiosity of the human spirit. After all, it's human nature to question, to explore, to seek answers to the most fundamental questions about our existence. As long as that spark of curiosity remains, the quest for a deeper understanding of reality will continue, pushing us to explore the universe and ourselves in ways we never thought possible. And perhaps, just perhaps, that understanding is closer than we think, hidden just beyond the horizon of our current knowledge. So, are we any closer to understanding the blueprint of the cosmos, or are we chasing shadows, tantalized by elegant equations that ultimately lead nowhere? Perhaps the answer, like the universe itself, is multifaceted. What if the very act of searching for a single unifying theory has blinded us to a deeper truth, a more nuanced reality that transcends our current understanding? Is it possible that string theory, despite its challenges, offers a compelling, even beautiful description of fundamental reality? After all, it presents a universe not of inert particles, but of vibrating strings, a cosmic symphony played out across dimensions we can barely imagine. Is that not a beautiful idea? The universe itself is music. Think of the Big Bang as the opening chord, a cataclysmic crescendo that set the stage for all that followed. The formation of galaxies, the birth and death of stars, the dance of planets around suns, all could be said to be movements in this grand cosmic composition. But what are we to make of the lack of tangible proof? The fact that we cannot directly observe these strings, that we cannot definitively test many of string theory's predictions, has led some to dismiss it as mere mathematical speculation. But perhaps we are asking the wrong questions, looking for the wrong kind of evidence. Perhaps the true value of string theory lies not in its ability to make specific predictions, but in its power to inspire new ways of thinking about the universe. It has challenged our assumptions, forced us to confront the limitations of our knowledge, and opened our minds to possibilities we never dreamed of. Is this not the essence of scientific progress? The constant questioning, the relentless pursuit of understanding, even in the face of seemingly insurmountable obstacles? Perhaps string theory is not the final answer, but rather a stepping stone, a necessary stage in our journey toward a deeper understanding of reality. Perhaps it is a flawed theory, destined to be superseded by something even more profound, even more elegant. But even if that is the case, its influence will endure. It has already reshaped the landscape of physics and mathematics, inspiring new generations of scientists to explore the mysteries of the cosmos. Imagine the universe as a vast, unexplored ocean. We have sailed on its surface for centuries, charting its currents, mapping its coastlines. But string theory has given us a glimpse beneath the waves, revealing a hidden world teeming with strange and exotic life. We may not yet have the tools to fully explore this underwater realm, but we know it is there, waiting to be discovered. The beauty and strangeness of viewing the universe as a symphony of vibrating strings, a concept that has captivated scientists and lay people alike, is something that cannot be denied. The idea that the fundamental building blocks of reality are not particles but vibrations, that the universe is essentially a musical instrument playing out its own intricate composition, is both awe-inspiring and deeply unsettling. Has string theory provided a compelling, even elegant description of reality? This has not been for a lack of trying. String theory describes a universe where all particles are made of incredibly small vibrating strings, and as such is said to be more fundamental than the point particle theories that are still in use. Despite what some scientists claim, it has yet to be proven that there are indeed only these tiny vibrating strings. Even though string theory still has a lack of experimental support that has led to a lot of its criticism, it would be wrong to count it as a complete failure. It is, after all, still a developing model and has made some progress over the years. What about the human quest to decipher the ultimate laws governing existence? This has been and continues to be a theme of countless people all throughout history. Is the universe music or mathematics, or perhaps something that has yet to be classified? It may be possible that it will never be fully understood by a human being, as they are, after all, limited to a certain point by their brain function. In the end, the quest to understand the universe is a human endeavor, driven by curiosity, ambition, and a deep-seated desire to make sense of the world around us. It is a journey filled with both triumphs and setbacks, with moments of clarity and moments of confusion. But it is a journey that is worth taking, a journey that enriches our lives and expands our understanding of ourselves and our place in the cosmos. The journey continues, and we continue to listen intently, seeking the notes of that unimaginable symphony that may just be the heart and soul of existence.